Paul, for the invitation. I'm all excited to share with you our experience in mapping and deformation of objects. All the more so since the work I'm presenting you today addresses a problem that has resisted to numerous research efforts for quite a couple of decades. This work is a joint effort of two research groups, Grid-Gen from Moscow and Pixel from Nancy, France. In my presentation, I will show you a couple of Python code. So you will find the code in the GitHub repo. I have sent a link to the chat. So let us start. My talk is centered on computing invertible maps. So I want to be able to associate any point of a geometric object with a point in a vector space. In other words, I want to map a surface to 2D space and a volume to 3D space. These maps are extremely useful in computer graphics since they allow to manipulate geometric objects as vector spaces. Here are few examples of applications that require such maps, and I imagine that you will recognize the images. Just for fun, I have picked 10 articles with MIT lab affiliation. As you can see, current map generation algorithms are quite sufficient in many cases. Nevertheless, it remains extremely difficult to guarantee the invertibility of the maps, especially when the constraints impose significant distortions, thus severely limiting the range of applications. It's our answer to this problem that I present you today. Let us go back in time for a moment to the origin of the problem. Maps were introduced to represent the surface of the Earth. In the end, it's merely a matter of scaling between the map and the Earth. But let us imagine for a moment that the Earth was not flat, but rather round. In this case, it would be necessary to cut it to make a topological disk, and then distort it to make a flattening. In this presentation, we assume that the cut is provided, and we will try to flatten the surface with a minimum of distortions, and especially no inversions. The most fundamental property we have to ensure is the invertibility of the map. And I cannot stress enough the importance of this property. The very idea of computing a map is being able to go back and forth between the map and object itself. Okay, my presentation is organized as follows. I will start by introducing the problem in 1D. We will see that it's rather trivial, but it will allow us to see the general approach of computing a map. Then we will encounter greater difficulties in 2D, and in the end of the 2D section, I will present the main idea of our approach. Here is an alarm clock, and I will make a wake-up call if you fall asleep, so you won't miss the crucial details. Finally, in the third section, I'll show the complete formulation of our approach with all bells and whistles. So, let us start with 1D. We want to compute a map between two blue segments. For the sake of simplicity, let us say that I want the map to be constrained at the boundary. Two curves shown here are two different maps, but only the green one is acceptable as it gives us a one-to-one correspondence between the segments. The red one is not good, is not acceptable because, for example, this point has 3 pre-images, and thus the map is not invertible. A very important question: how do we represent a map inside a computer? A very common approach is to represent it by simple functions defined over a domain cut in small pieces. For example, we can cut the domain in a number of small segments and define a map as a piecewise affine function. Now, let us write a simple program, because I'm a programmer, that maps one segment to another. Let us examine the following Python program. We start with a 16 elements array, and then we iterate through a very simple procedure. We replace each element with an average of its neighbors, and the first and the last elements are fixed in the array. What should we get in the end? Does it converge or oscillates infinitely? Well, intuitively, each peak in the array is cut out, and therefore the array will be smoothed over time. Here is an evolution of the data over time, and we converge to straight line segments. Is there a way to predict the result without guessing it and without executing the program? The answer is yes. And let us put the program aside for a moment, and let us recall how to solve systems of linear equations. Let us suppose that we have an ordinary system of linear equations. It can be rewritten by leaving xi at the left side of the equations. So I take x1 here, and all the rest goes to the right side. So we can rewrite it in this way. Then, suppose we have an arbitrary vector x0 approximating the solution, for example, a zero vector. Then, if we plug this vector in the right side of the equations, we can compute an updated approximation x1. Thus, we build a sequence of approximations, and under some assumptions on the system, this procedure converges to the true solution. This iteration is known as a GaussSedel method. Of course, there are other much more powerful numerical methods, but this is the simplest one. What is the connection to our Python program? It turns out that this program solves the following system with the GaussSedel method. If we consider the array as a sampled function, each equation here corresponds to a second-order finite difference. By solving this system, we compute a function with zero second derivative, and therefore the solution is a straight line. So there are two things to remember here. First, a map can be represented by simple functions defined over a mesh. And second, these simple functions can be obtained by solving a system of equations. Now, let us see less trivial examples. We are going to 2D. Imagine that we have a regular grid to map to a disk. Like in 1D, first we consider maps with constrained boundary. The red square is already mapped, the red square is already mapped to the circle. But what inside? What about the interior points? Well, we can try the solution we already have from 1D. We replace each element with a barycenter of its neighbors, leaving the boundary fixed. Look at this Python code. We define a regular grid, and then we perform a number of GaussSedel iterations, and for each interior node ij, we update its u and v coordinates. As we have already seen, this simple procedure corresponds to solving a discrete counterpart of Laplace's equation, that is zero second derivative with fixed boundary. Here, the partial derivatives are approximated by second-order finite differences. Note that if we map a boundary to a convex polygon, we have a guarantee to have no inverted elements by solving this simple equation. Okay, now it's the testing time, and this slide gives the outline of the 2D section of my presentation. We will see three different ways to build 2D maps that will be confronted with three test cases sorted by the order of difficulty. In all tests, we map a regular grid to different shapes. We have already seen that Laplace's equation allows us to produce a valid map from square to the disk. What if we shift the upper half of the boundary? The boundary polygon is no longer convex, and Tute's embedding produces inverted elements in this chicane. Here, there are inverted elements. If we map the square to a Z-shape, the problem becomes even more apparent. Here we have lost the invertibility of our map. Well, now let us try another approach. Instead of the direct map U of x, let us consider the inverse map x of u. This approach is less known in computer graphics community, but it's very common in the mesh generation for numerical simulations. And as you can see, it dates back to the 60s, the same time when Tute has published his famous paper, How to Draw a Graph. So the idea is to solve the same Laplace's equation, but for the inverse map. The difficulty, however, is that our unknowns are the vertices in the UV space and not XY space. With our variables, the Laplace's equations look like this, where G is the corresponding metric tensor. To actually solve this equation, as before, we can approximate the second-order partial derivatives by finite differences, and this results in a quasi-linear system to solve. For each node ij, the discrete system has two coupled equations. The green quotients here depend on the metric tensor. We can fix them, solve the system, recompute the quotients, solve another system, and so on. It's a quasi-linear system to solve. Here is a Python code that solves the system. It has exactly the same structure as before. First, we define a grid. We perform a number of GaussSedel iterations, and inside each iteration, for each interior node ij, we update its u and v coordinates. Let us test this code on our three test cases. The square is well mapped to the disk. The chicane also passes the test. There are no inverted elements. But the Z-shape still presents inverted elements. Note, however, that it's less dramatic than for the Tute embedding. Why? Why is the inverse map, why is the inverse harmonic map working better than the direct one? And can we improve the result? Let us consider the same things from a different perspective. We know that solving Laplace's equation delta u equal to 0, subject to appropriate boundary conditions, is equivalent to solving the variational problem of finding a function u that satisfies the boundary conditions and has the minimal Dirichlet energy. Here we denote by J the Jacobian matrix of the mapping U, the direct mapping. And you can see that if we apply Euler-Lagrange equations to the variational problem, we will get the Laplace's equation. But what about the inverse harmonic map? Let us try the same thing. After swapping the dependent and independent variables, Laplace's equation delta x equal to 0 is equivalent to the following variational problem, where under the integral we still have the trace of the metric tensor of the mapping u and not x, divided by Jacobian determinant. Of course, this construction is only valid if u is a diffeomorphism. This is important. On a mesh, we can try to solve the following problem. So we can reformulate the problem. We are looking for a minimum of an integral of a function f, where f is defined as follows. Note that the condition determinant superior to 0 comes from the fact that u of x must be a diffeomorphism to have the equality of the formulation. Well, this formulation gives a clear intuition about why optimizing for the inverse harmonic map is better than for the direct harmonic map. Imagine an algorithm. Imagine an algorithm for this minimization. If we have a valid initialization, in other words, a map with strictly positive Jacobian, and this is a big if, we can compute the Dirichlet energy, its gradient, and perform, for example, a simple gradient descent. The fact that we divide by the Jacobian determinant naturally creates a barrier. It means that if we start with a map without inverted elements, no elements will be inverted during the optimization phase. There are very solid theoretical results on invertibility of this energy in 2D and 3D, and this energy is a polyconvex hyperelastic energy to minimize. It's very well defined. The problem, however, that we do not have any practical way to minimize this function if we do not have a valid initialization in an untangled mesh. So let us put, and our contribution is an actual algorithm that allows us to solve for this equation without having a very good initialization. Before I give you the actual algorithm, let us see how it behaves. Let us test this formulation on our 3 test cases. And we can see that all 3 test cases are successfully passed. Indeed, a map is the square is well mapped to a disk. It's well mapped to a chicane, and the Z shape already behaves well as well. So now let us see how I have actually computed the maps, because I give you a solution to a problem, but we do not have a good algorithm to compute the solution. The main idea is pretty simple. We have a so-called Winslow functional, even if Winslow himself has never published a paper with a variational formulation. We can rewrite, as a slide of use of notations, we can rewrite the function f of g as follows. It will help us in a few seconds. This functional is well behaved for finite element methods, but we do not have any practical way to find the minimum if an initialization with positive Jacobian is not available. So here is the wake-up call. First of all, let us plot the max function. So I'm interested in this plot. If we plot max 0D, it looks like this. So let us define a regularization function, the function chi of d and epsilon. Check the function chi. As epsilon goes to 0, our regularization converges to the max function, while being perfectly smooth. Then we can rewrite the problem as follows. We are looking for the following limit, and this formulation already suggests an algorithm. So the idea is to build a decreasing sequence of epsilon values, and for each epsilon value, solve an optimization problem regularized by this epsilon. This simple idea gives us a way to recover from tangled initializations. Well, let us see the actual algorithm. In practice, the map U is piecewise affine and can be represented by the coordinates of the mesh. We can discretize the problem as follows. And then we start from an initial guess U0, and it can be a random initialization or even all mesh degenerated to one point. And then we build a sequence of approximations. And for every iteration, we must carefully choose the regularization parameter epsilon. And we solve a minimization problem for each given regularization epsilon k, and this can be done via Newton or quasi-Newton method. We have proven that an idealized minimization algorithm can untangle any mesh, well, if the solution exists, in a finite number of iterations. In practice, we witness less than 100 Newton iterations with a positive definite matrix. Here is the source code that I have used to produce the invertible maps we already saw on the test panel. As you can see, in mere 30 lines of Python, we can solve the problem. Of course, this particular code is not to be used in real-life applications because it is ridiculously slow for bigger problems. We will soon publish C++ code that is roughly twice or thrice the size of this one. In computer graphics, any claim about invertibility always faces a simple sanity check. Take a square and make 2 points inside the switch places. Here, all points shown in red are locked. Our method successfully avoids the desk reject, so we can proceed to the full formulation with all bells and whistles. Okay, the full formulation. First of all, we have the regularization function chi that we have already solved. Then we will define 2 distortion measures. We have already met the first one. F measures the shape quality of each element. Note 2 over d in the denominator. This formulation is unified both for 2D and 3D, so d is equal to 2 or 3. To regularize the function f, we modify the denominator. But in fact, in our optimization, we can mix different objectives. If we optimize for the shape function f, we can compute a conformal map. But we can also ask for the preservation of area of elements. The function g measures the area distortion. So when we minimize for a determinant plus 1 over the determinant, we want to compute a map whose determinant is whose Jacobian determinant is equal to 1. And we can regularize this function just like we did for function f. Finally, we combine both distortion measures through the trade-off parameter lambda.
Hey, Dmitry?
Yeah.
Oops, sorry. Can I ask a question? So you've mentioned polyconvex a few times. Can you define that and tell us what you mean? Like, are f and g convex functions? It's not obvious to me.
F and g are not convex. Those are polyconvex functions. Polyconvex is a generalization of the convexity. Mm-hmm. It means that these are not convex. These are polyconvex. It's a weaker notion. It means that there exists a convex function of minors. So a matrix function here. J is a matrix. Is a Jacobian of the map. So we have a function that takes a matrix as an argument. Mm-hmm. And well, it is polyconvex, the definition of the polyconvexity, that there exists a convex function of all minors of this matrix.
And what does that tell us about life? I'm sorry, I've never heard of this condition before.
Well, in particular, this implies rank 1 convexity.
Cool.
I don't know if you have heard about this one. Convexity implies polyconvexity. Polyconvexity implies rank 1 convexity. So these are generalizations. The function is not convex, but it's sufficiently well behaved.
Okay, cool, thanks.
So we have two measures. The measure F that allows us to estimate the shape quality of an element, and the measure G that allows us to measure the distortion of the area of the element. And we combine them, we will minimize a weighted function, a weighted sum, where lambda is a trade-off parameter between shape preservation and area preservation. Note here that this energy is polyconvex for epsilon equal to 0, and the polyconvexity is lost for epsilon superior to 0. But nevertheless, this method is amazingly robust. It works well both in 2D and 3D and is not limited to regular grids and simplicial meshes, because it's well defined even in continuous settings. Well, testing time. The time has come to test things seriously. Up to this moment, we have always talked about constrained boundary mappings, but our method works quite well with free boundaries. Here is an example of free boundary deformation. The left image shows the rest shape, and the middle and the right images are the compression and bend test respectively. The vertices shown in red are locked. All other vertices are free to move. The result is very intuitive for a human. Under compression, the object has chosen one of two possible configurations, towards the top or towards the bottom. And in the bend test, the object behaves exactly as it was made of some elastic material. But all this is derived from the theory of elasticity. So we rely on works by John Ball. We have a hyperelastic material here. Both our distortion measures are invariant to rotations, so check how the geometric details in the middle of the piece are nicely rotated. Here we illustrate the influence of the parameter lambda. So I have performed the three free boundary optimizations with different values of lambda. If we put lambda to 0, we are asking for an angle preserving map. So you can see that upon stretching, the triangles are forced, the area is triangles is forced to change to keep the angles. If we optimize with a large value of lambda, this corresponds to an ortholic or area preserving map. Note that the angles here are distorted, but the triangles keep the area constant. And finally, of course, we can ask for a shape area trade-off. So it's up to a user to define which value of lambda to choose. Back to the constrained boundary mapping. In last SIGGRAPH, so there is a very recent paper by Du et al. There is a benchmark that was published that contains a few thousands, several thousands of challenges, and this is one of the challenge. The Lucy mesh, this one, is mapped to a P-shaped domain by constraining the vertices shown in red. So we constrain the boundary. This test is basically to show that our method produces the same results on three very different initialization. Whether the initialization is random, where it's degenerate to one point, or produced by a Laplacian smoothing, we have the same, well, up to a numerical precision result. And the very nice paper that was published by Du et al., they have proposed a method that roughly minimizes the unsigned area of the mesh. And of course, all untangled meshes have the same area. So this is a problem. I mean, between this mesh and this mesh, they have the same unsigned area. So surprisingly, their method works the best in very complicated tangled configurations, and unfortunately converges to a zero Lagrangian when the solution is very close. Okay, here is just to show that we are able to process all the database published by Du et al. Last year. And to the best of our knowledge, our method and total lifted content, the method proposed by Du et al., are the only methods to have zero fails over the database. This slide shows quality plots of the resulting locally injective maps for every challenge from the database. Our results are shown in blue, where the results by Du et al. Are shown in red. Each dot corresponds to a quality of a corresponding map reduced to two numbers, the maximum stretch and the minimum scale. Well, long story short, we have zero fails on the benchmark, and we have a very good quality of the maps. This slide provides a log-log scatter plot of our running time versus mesh size for all the challenges from the database. So as you can see, for each run, the time varies from a fraction of a second to several minutes for the largest meshes. So this is a constrained boundary injective mapping stress test. We have generated an isotropic tetrahedral mesh of a cube subtracted from a larger cube. And we rotate the inner cube's boundary to test the robustness. Top row and the bottom row correspond to two different slices of the same mesh. Our LBFGS-based optimization scheme succeeds up to a rotation of 135 degrees, and we had to switch to the Newton method to reach 180 rotation. Note that 180 is particularly challenging because it's a saddle point of the elastic energy. We have two equivalent solutions of this problem. Okay, now for the limitations. It's important to note that even if the problem is well posed, a robust implementation may present significant difficulties. As I have already said, the quasi-Newtonian optimization scheme performs well for simple problems. It passes all the benchmark dataset. But it may fail for large deformations where Newton iterations are necessary. While our modified Hessian matrix is a symmetric positive definite, note that for stiff problems, the Jacobi preconditioned conjugate gradients can fail, and one may need the incomplete Koleski decomposition and beyond. In practice, we have found the method being very robust in 2D settings. We have not encountered a single practical test that we were unable to treat. In 3D, however, it can fail due to numerical challenges in very anisotropic and highly twisted meshes. It's not a limitation of the method itself, but to have a robust code when you have an anisotropy of factor 1000 can be very challenging. Well, you find the limit of double precision, for example. The second point is that inversion-free does not imply invertibility. Here is an example of an inversion-free map with two cases of non-injectivity when optimizing for a map with free boundaries. The map can present global overlaps, as well as the boundary can wind up around the boundary vertices. In other words, the total angle of the triangle incident to a vertex can be superior to 2 pi. Moreover, while being less frequent, a similar situation may occur on interior vertices. Typically, this situation happens near constraints causing a local compression of the shape. Well, it's possible to avoid all overlaps altogether by embedding our shape to optimize into an outer triangulation and performing a bimaterial optimization. In this case, no problems. Both the global and fold-2 coverings are prohibited by the fact that the outer material must not have inverted elements. If it is not an option, if a bimaterial optimization is not an option, we may need another thing to ensure local invertibility of a map. Let us illustrate the loss of invertibility, local invertibility, on a very simplistic mesh consisting of a single fan of 12 equilateral triangles. Let us flatten this surface with all vertices free to move. So this map is invertible, and it is what a user would normally expect, even if the shape of the triangles is far from being perfect, because in the start we had equilateral triangles. This map has a perfect triangle shape, but it contains inverted elements. You can see that when you go around the one ring, you change the direction of moving, so you have inverted elements, and thus this map is prohibited by our optimization. However, this map is free of inverted elements. And note that this map is also the global minimum of our energy, since all 12 triangles are perfectly equilateral. This map, however, is not invertible in one point, so it's a twofold covering, and it may be undesirable for user. How to fix the problem? Well, first, let us note that one rings of valence 3, 3, and 4 cannot be deformed to create a two covering. For 5 and plus valences, coverings are possible. Here is an example of two covering referred to the labels of the vertices. You can see, for example, that the triangle OAB is not inverted, and when you follow the boundary, you see A, B, C, D, E. This map is free of inverted elements. However, in this point, the map is not invertible. Of course, the same situation may appear for higher valences, and even we can have coverings for K superior to 2. We can fix this problem by reducing 5 and plus valence 1 rings to valences 3 and 4. For example, if we constrain the triangle AOD here, this triangle, if we constrain this triangle to have a positive area, we actually reduce this configuration to a 4 vertex 1 ring, effectively prohibiting all coverings. So this is a very neat solution because we do not have to tweak the optimization code. We simply pre-process the data by adding few more triangles to our mesh. In 3D, the problem is exactly the same. Here is the sum of dihedral angles incident to the edge MN is equal to 4 pi here. But if we cut the fan of tetrahedral by a plane, in fact, it corresponds to a 2D problem, So by adding 2 more tetrahedra to our model, we are guaranteed to prevent all coverings. Well, let us conclude. Until now, when we needed a parameterization free of folds, we used conformal maps. This solution works very well in unconstrained cases, but if you have constraints, the common approach is to fall back to Tute embedding, find an injective map whose distortion is to be optimized later. This method is even used in global parameterization despite the need for tedious surface cutting. With our solution, we can tackle these and other difficult cases without having to go back to maps to convex domains. We can directly change the objective function. We have a per triangle objective function, which is much less intrusive in applications. For example, we manage the 3D case is in the same way, which is of particular interest for hex remeshing. Here, for example, you can see that quad cover may need a backup solution for loss of local injectivity. And with our elliptic smoother, we do not have this problem. This works well. Here is another example. Interactive inversion-free deformations. This is a textured 2D mesh of an octopus, and we can apply directly our method. When the user constrains a vertex, the rest of the mesh moves to minimize its distortion as expected. Note that we can make a complete rotation to the tentacles without breaking the injectivity. So our mapping approach offers great prospects for applications which we are currently looking at. In particular, we are looking to improve global parameterizations, free boundary deformations, integration with other energies such as alignment with direction fields or generation of orthogonal maps. This concludes my talk, and once again, let me thank you for the invitation. I'm really excited to present our work. And if you have any further questions, I would be happy to answer them. Thank you.
Thanks for the talk. Yeah, I guess I can start with a question. You mentioned this thing about adding extra triangles near vertices of high valence. In order to prevent the double covering or triple covering issue. Can you do that for every single vertex and every single triangle at the same time? Is there a downside to, say, take every edge of the mesh and consider the mesh topology to be both its current topology as well as if you had flipped that edge?
Sorry, can you repeat the question? So you have the input mesh, and then what do you propose?
So the mesh topology is essentially a set of triangles, but
yeah,
you can augment that set of triangles with by taking every pair of 2 triangles that share an edge and constructing the edge flip of that. That produces a different set of 2 triangles.
The result is no longer. You can have so if you have 2 triangles like this and you flip the edge, you obtain a triangle with an inversion.
Right. Oops. That yeah, forgot about that.
So, and moreover, we are actually adding less triangles that you propose. We add in 1 or 2 in practice. We are adding 1 or 2 triangles per 1 ring. So it's really not that costly.
I see. Got it.
Well, that's a good question. I apologize if it's a little noisy. I have to step out to run an errand, but I'm watching on my phone. My understanding is that harmonic maps don't always exist when your target has positive curvature, right? Like the existence theory for harmonics map, usually they go the other way around, right? So I'm wondering if, like, because the source domain of your map is flat, is that enough to guarantee that there's a minimizer in the smooth case, or like, does that ever come up in practice? I don't know.
I did not. I didn't hear all the question. Can you try to repeat
I'm sorry
it, please?
about that. Yeah, of course, of course. So, like, you know, in differential geometry, there's all this theory about when harmonic maps exist from one domain into another. And my understanding is that when the target domain has positive curvature, you can run into trouble, right? Like they call it bubbling sometimes in theory. And I'm wondering if you've ever run into, I'm just curious, like from a practical perspective, if it matters, like, do you ever run into cases where like something doesn't converge as you refine your mesh or something because of this existence problem? Or
no. In our tests,
cool.
and we have performed thousands and thousands of tests, we were always able to find a solution if it exists.
If it exists.
And the existence of the minimizer, I don't know.
Interesting.
So,
okay, I wonder maybe it's.
So if there is a valid map that exists, we can find it. Whether it exists or not, it's a very theoretical question, and I'm a very practical guy. So
yeah, that's totally reasonable. Yeah, I'm just curious in practice. I guess it just doesn't come up. That's cool. It's nice to hear.
So can you talk a little bit more about how you prove the theoretical guarantees on the convergence of the algorithm? And also, well, I think I might have missed this, but I know that there's this epsilon parameter in the regularizer, and you said that you update it somehow. Is there
yes.
Is it important how you update it?
It's very important. It's crucial. Well, let's go back to the algorithm. Yep. So yeah, it's very, you need to choose the epsilon very carefully. And we have a formula. We tried to build in our, we have published an archive research report where we build a decreasing sequence of epsilon. We start with epsilon 0 equal to 1, for example, whatever. And then to choose the epsilon 2, the next value of epsilon, we have a formula that allows us to guarantee that the value of the function itself will decrease if you find a global minimum. So certain assumptions, I'm talking about certain assumptions and fine print here, is that we have a way to choose a sequence of value epsilon k. So we have a way to choose this sequence in a way for that the global minimum, for example, will be in the admissible set after a finite number of iterations. This is a consequence of our theorem. And so,
what do you mean by the admissible set here? The
admissible set, determinant superior to 0 in every point.
Okay.
So a feasible set is we have a valid inversion-free map. And this set can be, so we have a theorem, a proof, that if we use our formula to choose the epsilon k, an idealized, this is very important, an idealized minimization algorithm, and idealized, it means it actually minimizes the energy. For example, it will not be stuck in saddle points and stuff like that. For example, if you choose a minimal idealized minimization algorithm that already finds the global minimum, you are guaranteed to find the positive Jacobian map in a finite number of elements.
So is this related to like the central path in convex interior point methods? It sounds sort of reminiscent of that.
I do not see a connection, but it doesn't mean there is none. This I don't know.
And you said if the optimization algorithm finds the global minimizer for each choice of epsilon, then in a finite number of steps, you'll find an uninverted map. But what about, you mentioned this polyconvexity. Does that guarantee that you can find a global minimum of each
no.
sub-iteration?
No. In our theorem, you do not have to find the global minimum. It's a simple example of an idealization of the minimization toolbox. For us, it's sufficient to that the value function f of uk plus 1 is inferior to 1 minus sigma f uk, where u is the position of the vertices. If we have a minimization toolbox that guarantees that we have we minimize actually a function, this suffices for the method to converge. Normally, you should not be stuck in local minimums and stuff like this, because the regularization function, it's monotone, it's strictly monotone, it's partial derivative with respect to the epsilon, it's strictly monotone. So when you decrease the epsilon, your function will be growing. So if you are in a local minimum at some point, at some iteration k, at the iteration k plus 1, you are not anymore in a local minimum, because it increases. You change the steepness of the function when you decrease the epsilon. So I cannot tell you that if you will use a Newton method, you will never be stuck in a local minimum. I cannot. I do not have this guarantee. The theorem we were able to prove works on this assumption, that if we have a function and we have a toolbox that actually can minimize a function for a prescribed amount, percentage of the function, then you will converge. For example, the function, the minimization toolbox that gives you the global minimum will succeed, but we have weaker conditions on the convergence. So to sum up, in practice, I do not have any proof that a particular toolbox particular existing toolbox will find the will find the admissible map. However, in all our tests, we have succeeded.
Thank you. And then, okay, one more question. You mentioned that this is a hyperelastic energy and the relationship to a whole body of theory on elastic energies. So I know there must be many variations of elastic energies out there. What makes this one so special for this problem?
Well, it's not so special. The theory of John Ball, the paper I have cited, this one, works on a very large family of functions, and this particular one is not so special. It's just very cool to compute. It's very simple, and all the conditions from the theory by John Ball are satisfied. But you can use other things for sure.
Cool.
Thank you.
Well, I think we're at time. So let's give the speaker another round of applause.